In this video, we'll be discussing within the realm of acid-base chemistry how to calculate different locations along a strong acid, strong base titration curve. In any strong acid, strong base titration calculation, there are two factors that will affect your pH. One is the neutralization, essentially how much acid has been neutralized. How much base did you add? That's the amount of acid that was neutralized. And because we are adding a liquid from the base into the acid solution, we also are diluting it. So by adding any liquid, whether it be a base or if we just added water, we would be reducing the concentration of the original acid, which will affect the pH. Typically, the dilution is not as important as the neutralization, but it is still something that we need to take into account. On any titration, there are four locations that we need to be able to calculate. The first is the starting point, which is the location before we've added any of our strong base, if we're doing a strong acid, strong base titration. The equivalence point, that's the location where we've added the exact same number of moles of base as we had original acid. The half equivalence point, which is halfway to the equivalence point, so you've added half the number of moles of base as you originally had acid and, well, everywhere else. So for that, you need to figure out how much base have you added. Has it neutralized all the acid? If so, then how much extra base do you have? Or if you've added less base than acid, how much base have you added? How much acid did that neutralize? And then you need to take into account dilution. So to show some of how you do these calculations, we're going to look at the following example. A student is doing a titration of 10 mils of a 0.20 molar hydrochloric acid solution, which is a strong acid, with 0.25 molar sodium hydroxide. Sodium hydroxide is a strong base. So we'll look at the pH at the starting point, the pH at the equivalence point, pH at the half equivalence point, and then we'll just pick a random location, 3 mils along the titration, and figure out what the pH is at that location. Looking at the first of these examples is the location on our titration curve before we have added any of the strong base. So we're looking at a student is essentially having 10 mils of a 0.2 molar hydrochloric acid solution. What is the pH of that solution before we add anything? Well, because we're working with, in this case, a strong acid, HCl, the strong acid tells us that the concentration of our H plus solution is equal to the listed concentration of our strong acid, right? For a strong acid, it completely disassociates into, in this case, H plus and Cl minus. So the concentration of our H plus will be 0.20 molar. To find the pH, pH is equal to the negative log of our H plus concentration. So that would be the negative log of 0.20, which would be equal to 0.69797. In terms of significant figures, we're taking the log of a value that has two significant figures, and so our value will have two decimal places. So our pH is going to be equal to 0.70, right? We're rounding it right there. Next, we're going to do the calculation for the equivalence point. Now, because there are two components that we need to take into account with any of these titration calculations, the neutralization and dilution, at the equivalence point, we have neutralized all of the acid. There is none left over. We also have no excess base. That's the definition of the equivalence point. But we need to figure out what the volume is that we've added. So to figure out the volume, what we will do is figure out how many milliliters of our 0.250 molar sodium hydroxide do we need to completely neutralize 10 mils of a 0.2 molar solution. So what we'll do is we'll use 0.20 moles of H plus. We're writing H plus because it's a strong acid and it breaks apart completely. So this is per liter of H plus. We have 10 mils, so 0.0100 liters of our acid solution. Our liters of acid solution cancel out. So now we have moles of H plus. This is the number of moles that we need our base to neutralize. It is a 1-to-1 mole ratio. So 1 mole of our OH or our NaOH solution is going to neutralize 1 mole of our H plus. The moles of H plus cancel out. So we're now left with moles of OH minus. So we will have the 0.25 moles of OH on bottom per 1 liter of our OH or NaOH solution. Our moles cancel out, giving us liters. So this will tell us how many liters of the sodium hydroxide solution that we need. You'll find that this comes out to be 8.0 times 10 to the negative third liters. So the volume of NaOH that we need is 10 to the negative third liters, or 8.0 milliliters. Now, for a strong acid, strong base titration, the equivalence point pH is exceptionally easy to figure out. Because we have neutralized all of the acid and have no excess base left over, the concentration of our H plus, the only location where we're getting that from is from the water. And if we're working at 25 degrees, then the concentration of the H plus is that of water, which would be 1 times 10 to the negative 7. So our pH would be equal to 7.00. So that's our pH, and that is the amount of base that we have to add. Next, we're going to find the pH at the half equivalence point. So in our previous problem, we worked out the volume to get to the equivalence point. The volume to get to the half equivalence point is 1/2 of that value. So we initially had 8.0 milliliters is required to get to the equivalence point. If we take that value times 1/2, that would get us the volume needed to get to the half equivalence point, which would be 4.0 milliliters. Now, whenever we're doing one of these calculations, there are two things to take into account: the neutralization and the dilution. So the half equivalence point is the place where you've neutralized 1/2 of your original acid. So if we calculate the number of moles of original acid, we can just take that number and divide it in half. So the number of moles of original acid that we had, the initial value was equal to 0.20 moles per liter times our 10 mils. So this would be 0.0020 moles of H plus. That's the initial amount that we have. The half equivalence point is 1/2 of that value. We've essentially neutralized half of it. So the number of moles at our 1/2 equivalence point for our H plus would be equal to 1/2 of this value. So we could take this divided by 2, and that would give us 0.0010 moles of H plus. Now, our concentration of H plus, concentration is moles over volume, and so we would take our 0.0010 moles, divide that by our new total volume. So we started out with 0.0100 liters, or 10 mils, and we added to that our 4 mils of base. So we've in essence diluted our solution down. So that will give us 7.142857 times 10 to the minus 2 molar. Now, the pH is equal to the negative log of that value. In terms of significant figures, we would have 2. So our value is going to have 2 significant figures. Our pH would be equal to the negative log of our H plus concentration. So a negative log of 7.1429. We just need to keep a couple extra sig figs to prevent a rounding error. That would be 1.14613. We had 2 significant figures, which means we will have 2 decimal places when we do our pH. So our pH would be equal to 1.15. In our last calculation, what we're going to do is we're going to try to determine the pH at any location along the titration curve. So we've just selected 3 as our value. So we need to take 2 things into account: neutralization and dilution. To do the neutralization, we first need to figure out how many moles of sodium hydroxide have we added. So that would be our 0.25 moles of OH of our sodium hydroxide per liter of our sodium hydroxide times the volume that we added, 0.0030 liters of OH minus. Liters of OH minus cancel out, and so that's going to give us 7.5 times 10 to the negative 4 moles of OH minus. So essentially this is the number of moles of acid that we have neutralized, right? Any moles of base that we add, it's going to neutralize the exact same number of moles of acid. So this value here is the number of moles of acid that has been neutralized by adding 3 mils of our 0.25 molar sodium hydroxide solution. So we now need to figure out the number of moles that we initially had of our H plus. So that's 0.20 moles per liter of our H plus times our 0.0100 liters. Liters cancel out, giving us 0.0020 moles of H plus. Okay, so our number of moles now of our H plus is going to be equal to the number of moles of H plus that we started out with minus the number of moles of OH minus that we added. So this would be 0.0020 minus 0.00075, which would be equal to 1.25 times 10 to the negative 3rd. So our H plus concentration would be, because we're looking at concentration, that's moles per volume. So that would be equal to the number of moles of H plus, 1.25 times 10 to the negative 3rd, divided by our volume. We started out with 10 mils, so that's 0.0100 liters, plus, and then we added 3 mils, so 0.0030 liters. Plug this into your calculator and you'll get 9.615 times 10 to the minus 2nd molar. Our pH is equal to the negative log of our H plus concentration. So that would be the negative log of our value, which would be equal to 1.017. Our value here that we were plugging in had two significant figures. From this subtraction, this value will have two significant figures. So this will have two, meaning that our number here that we end up with is going to have two significant figures. If we're taking the log of a value that has two significant figures, then it has two decimal places. And so this will be 1.02 would be our pH. Now, if we're doing a similar process, but this time we're putting a strong base at the bottom and a strong acid at the top, you would do the exact same process that we just did, taking into account the neutralization and the dilution, but instead of first calculating the pH, we would be calculating the OH minus concentration, and so you would be calculating the POH. You can always go from POH to pH by taking the pKw, which is 14, minus the POH is equal to the pH. So we would, if we were doing a strong base, strong acid titration, we would first calculate the pOH, and then 14 minus the number that we calculate gives us the pH.